Hello everybody, my name's Ben, this is Math with Ben, and today I would like to talk to you about my favorite derivations. Now I know I said last video that today I'd be talking about integrals and the fundamental theorem of calculus, but I would rather today talk about one of my favorite derivations, and that is the derivation of charge as a function of time as a discharging capacitor in a simple resistor capacitor circuit. Now, also, next video for the calculus series, instead of doing integrals and the fundamental theorem of calculus, I will instead be continuing to talk about derivatives because I realize there's more than I talked about, right? I already knew there was more than I talked about, but there's some things I need to go over. So let's talk about an RC circuit. So what is an RC circuit? Well, a circuit is a circuit with one resistor. With a simple RC circuit is a circuit with one resistor let me draw it here. And one capacitor. I'm not the best at drawing, sorry. So this is an RC circuit, and here we have a battery, which is applying some potential difference V, and here we have a resistor with resistance R, and a capacitor with capacitance C. Now, there's something in electricity and magnetism called Kirchhoff's loop rule. And this states that the net potential difference of a circuit is equal to 0. Now, what this means for us in our simple RC circuit here is that the voltage of the battery, VB, minus the voltage of the plus the voltage of the resistor, plus the voltage of the capacitor is equal to 0. Now, let's talk about what a resistor and a capacitor do. A resistor resists the motion of charges, right? That's implied in the name. In a constant voltage circuit, the resistor lowers the motion of charge. And we can see this in Ohm's law. Now, what is Ohm's law? Well, Ohm's law states that the voltage in a circuit with one resistor is equal to the current, which is I, times the resistance R. And this also states that, right, V is equal to dQ dt times R, because current is just the change in charge with respect to time. It's the amount of charge flowing through some cross-section with respect to time. And we can replace this here into our equation, right? And in this case, it's negative. The voltage is negative. The resistor, in this case, because we're saying there's a constant current, so the resistor can either decrease the current or decrease the voltage in a circuit. And in this case, we're saying it is decreasing the voltage because we need to have a net voltage of 0. So we still have VB minus, right, because it's decreasing the current, the voltage, minus dQ dt times R plus VC equals 0. Now, what is the capacitor doing? Well, the capacitor is the voltage of the capacitor, VC, is equal to the charge of the capacitor divided by the capacitance. Now, capacitance is a specific property of every capacitor, and it just is it's a property, right? Now, a capacitor, what it does is it builds up charge on the surfaces of plates. Once you connect a circuit and a capacitor in a circuit, the charge, the potential difference that is creating an electric field which creates the flow of charges is building up charges on the plates of the capacitor. Now, there is a limit to the amount of charge you can have on a capacitor plate. And once you've reached that, it closes off the circuit. And that's when you can remove the battery and the capacitor acts as the battery for a very, very short amount of time, because capacitors store electrical energy in form of electric fields instead of batteries, which store energy in form of chemical energy. But that doesn't, it does not matter for this derivation that much. So now we can place this in here into this equation. And again, that's negative because it's decreasing the amount of voltage in the total circuit. So we have VB, I'm going to do it over here, VB minus dq dt times R minus Q over C is equal to 0. And this is where the actual derivation begins. And this is where understanding the physics of it is less important for now, because you just need to understand how to do the math. The first thing we're going to do is move this whole term over to the other side. So we get VB minus Q over C is equal to dq dt times R. Now, this is a differential equation. It's a very simple one and a very easy to solve one, but it is a differential equation. So let's walk through the steps of how to get a function of charge in terms of time. So the first thing we're going to do is put this left-hand side into one term. How we can do that is we can multiply VB by C over C, getting us a common denominator, and that's going to be equal to CVB minus Q over C is equal to dq dt times R. And the next thing we're going to do is try and get the Q terms on the side with dq. So how we can do that is we can divide CV minus Q over to the other side. At the same time, I'm just going to make a two-step algebra move and move R over to the other side by dividing by it. So we're going to get 1 over RC is equal to dq dt times 1 divided by CVB minus Q. And then, now, what I didn't talk about in the derivatives video is that the derivative is an operator. Now, I talked about what operators were in my first video on limits, but this is an operator. It's not a fraction, right here. It's not a fraction. You cannot treat it as such. In this case, we will sort of be using it like a fraction. Now, I am not advanced enough in math to tell you why we can do this, but I can tell you that you can move each term of the derivative over to different sides in order to be able to make it integratable functions, right? So we can move this dt to the other side, and we get 1 over RC dt is equal to 1 over CVB minus Q dq. And now this is a integratable equation. We can integrate both sides to solve this equation. So let's do that. Let's integrate this side from 0 to t, and integrate this side from 0 to q. Oops. And we can move this back up here. Just going to rewrite it. 0 to t of 1 over RC dt is equal to 0 to q, 1 over CVB minus q dq. Now, I haven't talked about integrals yet, but these ones are very easy to solve, okay? And I will explain this more when I do a video on integrals, but all I tell you right now is that the solution to these integrals and how we can do them is this. This will make a t, so we do t over RC, t divided by RC. And again, you don't need to know this. It's just some cool math. Is equal to, this is a little bit more complicated of an integral. What we can do, right, when we have this is we can do what's called U substitution, and this is a function on the bottom of a fraction in a integral. To make it simpler, we can do 1 over u, where this is all u, times the derivative, which is just 1 in this case because it's in terms of q. And like we said last time, any derivative where it's just one variable with 1 as its coefficient is just 1, but there is a negative in front of it. So the derivative of, or the integral of 1 over u is ln, but there's a negative here. So we have negative natural log of CVB minus q from 0 to q. And we can plug in these bounds. Again, this math is not too important to know. It's just kind of a beautiful and simplistic derivation that leads to a very, very beautiful answer. And this is negative ln CVB minus q minus negative ln CVB, because when you plug in 0, it's just 0. And before you say we can make this a plus, I'm not going to do that. What I'm going to do first is move a negative to the other side. So we have negative t over RC is equal to the natural log of CVB minus q minus ln of CVB. And now this is where log rules come into play. The first thing we can do is when we have log minus log, we can just do log of the first term over the second term. So this will be negative t RC equals ln of CVB minus q divided by CVB. And then to get rid of a log, this is again a log rule. When you have ln, which is just log based e, to cancel it, you can just take everything to the power of e. So we're going to take this side to the power of e to the negative t over RC is equal to e to the power of ln CVB minus q divided by CVB, where these two things will cancel and we just get e to the negative t over RC is equal to CVB minus q over CVB. And now this is looking like a much, much, much more friendly equation than what we had earlier. And so first thing we can do is move this to the other side, and we can get, I'm going to move back over here, and we can get CVB times e to the negative t over RC is equal to CVB minus q. I can move the q to this side, and I can move this whole term to the other side by just subtraction. And so we get q, I'm going to move down here. Q is equal to CVB minus CVB e to the negative t over RC. And then I can factor out a CVB, and we get Q is equal to CVB times 1 minus e to the negative t over RC. And this is beautiful, right? This is a very elegant equation compared to what we had earlier. And this Q is actually a function of time. We can see that, right? There's a t right there. So what we can do now is say this is equal to Q as a function of time is equal to CVB times 1 minus e to the negative t over RC. And then what we can do is this CVB may look familiar, right? We said earlier that V of a capacitor is equal to Q over C. So if we multiply the C over, we get Q is equal to C times V, where in this case, because it's the voltage of the battery, this is where the voltage of the capacitor is at max, meaning you will have the maximum amount of charge on that capacitor that you can have. So this is just Q max. So we get Q of T is equal to Q max times 1 minus e to the negative t over RC. And this is truly beautiful. Now, I want you to do something on your own and plug in tau, where tau is the time constant of an RC circuit, and it's equal to RC. You can see, I'll give you a hint, that if you plug it in, you get Q of tau is equal to Q max times 1 minus e to the negative 1. and find out what percent of Q max you will have left as the capacitor discharges over tau. And you can see after around 4 taus, around 4 time constants, the total charge on the capacitor will be around 0. Yeah. And this is a really, really, really beautiful derivation. And it's one of my favorites, and that's just why I wanted to show you it. And this is our final answer. Q as a function of time is equal to Q max times 1 minus e to the negative t over RC. Thank you. This has been Math with Ben. Next time I will continue my thing about my series on calculus. And I hope you have a good rest of your night.